The universe is a vast, interconnected machine, governed by a set of rules that we are only beginning to understand. From the smallest particle to the largest galaxy, everything is tied together by the fabric of space-time. This fabric is not just an abstract concept, it is the very stage on which the cosmic drama plays out. Space-time has been active since the beginning of everything, and is the key to the evolution of everything. To understand how the universe works, we have to understand how space-time behaves, how it was born, how it shapes matter, and how it will ultimately determine the fate of all that exists. The story begins 13.8 billion years ago, in a moment that defies ordinary logic. There was no space, no time, no matter, just a singularity of infinite density and temperature. Then, in an instantaneous flash, our universe burst into existence. This was the Big Bang. At that very instant, space and time were created. The infant universe was a tiny speck of energy, far smaller than an atom, yet it contained all the potential for everything that would ever be. In the first fraction of a second, something remarkable happened. Inflation. The universe expanded faster than the speed of light. Now, you might think that violates Einstein's rule that nothing can travel faster than light, but here's the crucial point. Nothing was moving through space faster than light. It was space itself that was expanding. Imagine a balloon being blown up. The points on its surface move apart, but they aren't moving across the surface. The surface is stretching. That's what inflation did. In less than a trillionth of a second, the universe grew from subatomic to the size of a baseball. And it didn't stop there. It continued to expand, though at a much slower rate, ever since. During this rapid expansion, tiny quantum fluctuations were stretched to cosmic scales. These fluctuations were incredibly subtle, differences in density of just 1 part in 100,000. But they were enough. In some regions, matter was ever so slightly more concentrated. As the universe cooled, energy transformed into particles, and these denser regions began to pull in more matter through gravity. Gravity, as Einstein taught us, is not a mysterious force acting at a distance. Gravity is the curvature of space-time itself. Any object with mass bends the four-dimensional grid of space and time around it. The more mass, the deeper the curvature. A star bends space-time around it, causing light to follow curved paths. A planet does the same on a smaller scale. Even you, right now, are bending space-time, though the effect is minuscule. In the early universe, these slight density variations grew as gravity pulled matter together, forming the first stars and galaxies. The cosmic web of filaments and voids that we see today is the direct result of those initial quantum seeds, amplified by the expansion of space and the relentless pull of gravity. But gravity, when taken to the extreme, becomes something terrifying: a black hole. Black holes are the universe's ultimate monsters. They form when massive stars run out of fuel and collapse. A star that burns for millions of years can die in seconds. The core implodes under its own weight, and the outer layers crash into it, triggering a supernova explosion that outshines entire galaxies. What remains is a dead core so dense that its gravity becomes overwhelming. The escape velocity exceeds the speed of light. Not even light can break free. That's why they're black. For decades, scientists could only infer their existence indirectly, by observing the effects of intense gravity on nearby stars and gas. Black holes themselves emit no light, but when they feed on surrounding material, that matter heats up to millions of degrees and emits powerful X-rays. Telescopes like the New Star Observatory have detected these X-ray signatures, allowing astronomers to measure the mass and orbit of invisible objects. In a globular cluster called 47 Tucani, a star was seen being ripped apart by a dark, dense companion. The object had the mass of a giant, but was tiny, a prime candidate for a black hole. Yet size and mass alone aren't proof. There's another kind of ultra-dense object, a neutron star. Neutron stars also form from supernovae, but they lack the mass to completely collapse into a black hole. Their gravity is enormous. They can pull in gas and dust, but light can still escape. The only way to be certain that an object is a black hole is to go beyond the electromagnetic spectrum. That's where gravitational waves come in. When two black holes collide, they create ripples in spacetime that propagate across the universe at the speed of light. These ripples were first detected in 2015 by the LIGO observatories. The signal, a faint chirp, matched exactly what Einstein's equations predicted for a merger of two massive black holes. For the first time, we could hear the universe. Gravitational waves have now been used to confirm numerous black hole mergers, providing the ultimate proof that these cosmic beasts not only exist, but that they are common. Every time a black hole merger happens, it sends a ripple through space-time, revealing secrets about the most extreme environments in the cosmos. But black holes are just one consequence of how space-time works. Understanding space-time means understand gravity, and gravity shapes everything from the orbits of planets to the expansion of the universe itself. Einstein's general relativity describes gravity as the curvature of space-time caused by mass and energy. This curvature determines how objects move. The more mass, the deeper the curve. But there's a twist. Space-time can also be stretched and twisted by rotating masses. This phenomenon, called frame dragging, is subtle around planets, but becomes dramatic near black holes. In theory, if you could warp space-time severely enough, you might create closed time-like curves, loops that allow travel into the past. That's the stuff of science fiction, but it's grounded in real physics. However, even if such loops exist, they don't allow you to change the past. The block universe model suggests that past, present, and future all coexist as a four-dimensional block. Time travel would simply allow you to visit other slices of that block, but you cannot alter what is already there. This is why Stephen Hawking's Party for Time Travelers, held in 2009 but announced only after the fact, had no attendees. In the block universe, no one attended, so no one ever will. One of the deepest mysteries about time is why it flows only forward. We remember the past, but not the future. Eggs break, but never unbreak. This arrow of time seems to be linked to entropy, the measure of disorder. The universe started in a state of extremely low entropy. The Big Bang was highly ordered, all the energy and matter packed into a tiny, uniform hot point. But as the universe expanded, entropy increased. Stars formed, galaxies clumped, and eventually everything will drift apart, becoming cold and dark. This increase in entropy is the reason time has a direction. It's not that time itself is moving forward, it's that the universe is evolving from low entropy to high entropy. And this is why we can't travel backwards without violating the second law of thermodynamics. While we contemplate the grand scale of space-time, we must also consider the more immediate environment of our solar system. The sun is our local powerhouse, but it also protects us. it emits a stream of charged particles called the solar wind, which carves out a magnetic bubble around the entire solar system known as the heliosphere. This bubble acts as a shield against galactic cosmic rays, high-energy particles that zip through interstellar space at nearly the speed of light. These cosmic rays come from supernovae and other violent events. They can damage DNA and cause mutations. In fact, cosmic rays have been a driving force in evolution, creating the genetic variation that natural selection acts upon. Without them, life might not have diversified. But too much radiation is deadly. The heliosphere deflects most cosmic rays, and Earth's own magnetic field and atmosphere provide additional protection. Without these shields, the surface of Earth would be a barren, irradiated wasteland. Out beyond the heliosphere lies the Oort cloud, a vast shell of icy bodies that marks the boundary of interstellar space. The Sun's gravity loosely holds these comets, but occasionally a passing star can perturb the Oort cloud, sending a shower of comets into the inner solar system. Astronomers use the Gaia spacecraft to track nearby stars and predict close encounters. One such star, Gliese 710, is on course to pass through the Oort cloud in about 1.3 million years. That could trigger an increased rate of impacts, a reminder that our solar system is not isolated but part of a dynamic galactic neighborhood. Moving beyond our solar system, the search for other worlds has revealed astonishing diversity. The Kepler mission and other surveys have discovered thousands of exoplanets. Most are nothing like Earth. We've found super-Earths, hot Jupiters, and sub-Neptunes. One particularly intriguing world is GJ 1214b, about 40 light-years away. It's sometimes called a water world because it may be composed of up to 70% water by mass. But too much water might be a problem for life. On Earth, life needed interaction between land and oceans, chemicals from rocks dissolving in water. On GJ 1214b, the ocean may be thousands of miles deep, with high-pressure ice sealing off the rocky core. Without that nutrient exchange, life may never get started. It's a reminder that the Goldilocks zone isn't just about temperature. It's about the right balance of water, land, and geology. Closer to home, the moons of our solar system are even more fascinating than the planets. Saturn and Jupiter each have over 60 moons, each a unique world. Take Iapetus, a moon of Saturn with a bizarre two-toned appearance. One side is as dark as asphalt, the other bright as snow. The Cassini spacecraft revealed that dark dust from a distant moon, Phoebe, drifts inward and coats the leading hemisphere of Iapetus. That dark side absorbs more sunlight, gets warmer, and causes ice to evaporate. The vapor then freezes on the colder trailing side, making it whiter. It's a runaway process that creates a yin-yang moon. Even stranger, Iapetus has a mountain range that encircles its equator, rising over 12 miles high, taller than Everest. That ridge may have formed from a ring of debris that once orbited Iapetus and then collapsed onto its surface. Then there's Enceladus, a tiny moon of Saturn. When Cassini flew by, it spotted geysers of water vapor shooting hundreds of miles into space. These geysers come from a subsurface ocean of liquid water, kept warm by tidal heating. Saturn's gravity squeezes and stretches Enceladus as it orbits, generating friction heat. That heat keeps the ocean from freezing. Cassini sampled the plumes and found salty water, organic molecules, and even complex hydrocarbons. Enceladus has all the ingredients for life. The question is whether life actually exists in that dark ocean. Future missions aim to find out. Titan, Saturn's largest moon, has a thick nitrogen atmosphere and landscapes eerily similar to Earth: rivers, lakes, and dunes. But those rivers are liquid methane and ethane, and the dunes are made of organic sand. Titan's chemistry is rich with the building blocks of life, though the extreme cold, 290 degrees Celsius, makes water-based life unlikely. Still, it's a world where we might find a completely different form of life, one based on methane. That would be a profound discovery, showing that life can arise in many different environments. Our own moon has a history just as dramatic. It formed from a catastrophic collision between the early Earth and a Mars-sized protoplanet called Theia. The impact was so energetic that it vaporized both bodies, creating a giant donut-shaped cloud of molten and vaporized rock called a synestia. Over hundreds of years, this cloud cooled and condensed. The Earth reformed at the center, and the Moon coalesced from the outer ring. That explains why the Earth and Moon have nearly identical compositions. They were mixed together in that fiery cloud. After formation, the Moon was covered in lava seas, and volcanic eruptions released gases that created a temporary atmosphere. For a brief window, about 3.5 billion years ago, the Moon may have had liquid water on its surface. But with only 1/50th of Earth's volume, the Moon's core cooled quickly. Its volcanoes died, its atmosphere drifted away, and any potential life would have perished. However, the Moon isn't as dead as we thought. Apollo seismometers recorded moonquakes, thousands of them. Most were from asteroid impacts, but 28 were shallow quakes of magnitude up to 5. These quakes originate about 15 miles underground, and they correspond to young features called lobate scarps, faults where the crust has thrust upward. The reason? The Moon is shrinking. As its interior cools, it contracts, and the brittle crust breaks under stress. These moonquakes and scarps are the Moon's death rattle. It's a reminder that even seemingly dead worlds can still be geologically active in subtle ways. The universe works through a constant interplay of forces: gravity, electromagnetism, and the nuclear forces. But the most dominant force on cosmic scales is gravity. It built the stars, the galaxies, and the black holes. It shaped the orbits of planets and moons, and it will eventually determine the ultimate fate of the cosmos. As the universe expands, entropy increases. Stars will burn out, galaxies will drift apart, and eventually the universe will become a cold, dark, and empty place. That is the heat death, the final state of maximum disorder. But that is trillions of years away. For now, we live in a vibrant, active universe, full of mysteries waiting to be solved. Every new discovery, from gravitational waves to ocean worlds, pulls back the curtain a little further, revealing the elegant machinery that runs it all. The story of how the universe works is still incomplete. We don't know what dark matter and dark energy are. We don't know if time travel is possible. We don't know if we are alone. But the journey of discovery is itself a testament to human curiosity and ingenuity. From the Big Bang to the death of black holes, from the birth of stars to the evolution of life, the universe is a story of constant change and unfathomable beauty. And we are part of that story. The universe works through a constant interplay of forces: gravity, electromagnetism, and the nuclear forces. But the most dominant force on cosmic scales is gravity. It built the stars, the galaxies, and the black holes. It shaped the orbits of planets and moons, and it will eventually determine the ultimate fate of the cosmos. As the universe expands, entropy increases. Stars will burn out, galaxies will drift apart, and eventually, the universe will become a cold, dark, and empty place. That is the heat death, the final state of maximum disorder. But that is trillions of years away. For now, we live in a vibrant, active universe full of mysteries waiting to be solved. Every new discovery, from gravitational waves to ocean worlds, pulls back the curtain a little further, revealing the elegant machinery that runs it all. The story of how the universe works is still incomplete. We don't know what dark matter and dark energy are. We don't know if time travel is possible. We don't know if we are alone. But the journey of discovery is itself a testament to human curiosity and ingenuity. From the Big Bang to the death of black holes, from the birth of stars to the evolution of life, the universe is a story of constant change and unfathomable beauty. And we are part of that story. Yet the most profound unknown lies just beyond the reach of our telescopes. Dark matter, the invisible substance that makes up about 85% of all the matter in the universe, holds galaxies together with its gravitational pull. We cannot see it. It does not emit, absorb, or reflect any light. But we know it exists because of the way galaxies rotate. The stars at the edges of spiral galaxies move far too fast to be held in place by the gravity of visible matter alone. Something unseen is providing the extra gravitational glue. The leading theory is that dark matter is made of weakly interacting massive particles, or WIMPs, that rarely interact with normal matter except through gravity. Underground detectors, miles beneath the Earth's surface, are trying to catch a faint signal from a passing WIMP. So far, silence. Other ideas suggest that dark matter might be made of primordial black holes formed in the first instance after the Big Bang. These tiny black holes, no larger than an atom, but weighing as much as a mountain, could swarm through the galaxy. They would be nearly impossible to spot directly, but their gravitational effects would mimic the presence of a vast, invisible mass. The hunt for dark matter is one of the greatest quests in modern physics. If we find it, we will finally understand what holds the cosmic web together. Even more baffling is dark energy. In the late 1990s, astronomers studying distant supernovae expected to find that the expansion of the universe was slowing down due to gravity. Instead, they discovered that the expansion is accelerating. Something is pushing the universe apart, counteracting gravity. That something is dark energy. It makes up about 70% of the total energy density of the universe. Its nature is a complete mystery. It could be a property of space itself, a constant energy that permeates the vacuum. Or it could be a new field, akin to the one that drove inflation in the early universe. Whatever it is, dark energy will determine the ultimate fate of the cosmos. If it remains constant, the universe will expand forever, growing colder and emptier until even atoms are torn apart. If it increases over time, the acceleration might become so violent that it rips galaxies, stars, and even space-time itself to pieces in a big rip. If it weakens, the expansion could eventually reverse, leading to a big crunch, where the universe collapses back into a singularity. Which destiny awaits us, we do not yet know. Between the extremes of dark matter and dark energy lies the everyday realm of stars. Our sun is a typical star, but it has a finite life. In about 5 billion years, it will exhaust its core hydrogen and begin to swell into a red giant, engulfing Mercury, Venus, and possibly Earth. After that, it will shed its outer layers, leaving behind a glowing ember called a white dwarf. This is the fate of most stars. But stars much more massive than the Sun will end their lives in a spectacular supernova, leaving behind either a neutron star or a black hole. The most massive stars, those over about 30 times the mass of the Sun, may collapse directly into a black hole without a visible supernova, a process that astronomers are only beginning to understand. Some of those black holes may be the seeds that grow into the supermassive monsters at the centers of galaxies. Our own galaxy, the Milky Way, harbors a supermassive black hole called Sagittarius A at its core. It has a mass of about 4 million suns squeezed into a region smaller than our solar system. When stars stray too close, they are ripped apart by tidal forces, creating brilliant flares. The black hole itself is quiet now, but it may have been active in the past, blasting out jets that shape the galaxy. Someday, in about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy. The two galaxies will merge, and their central black holes will spiral together, eventually becoming one. That merger will send gravitational waves rippling across the universe. The diversity of galactic collisions is staggering. Some galaxies are ripped apart by the gravitational pull of larger neighbors. Others are cannibalized, their stars and gas absorbed. The largest galaxies in the universe, the giant ellipticals, likely formed through a series of such mergers. They contain trillions of stars, and at their hearts sit the most massive black holes known, billions of times the mass of the Sun. These monsters are the engines of quasars, the brightest objects in the universe. A quasar can outshine an entire galaxy, powered by gas falling into the supermassive black hole at its core. That gas is heated to millions of degrees, generating intense radiation. The energy released can blow away the surrounding gas, starving the black hole and quasar of fuel. This feedback loop regulates the growth of both the black hole and the galaxy itself. Beyond galaxies, the largest structures in the universe are clusters of galaxies bound together by gravity. The Virgo cluster, about 54 million light-years away, contains over 1,300 galaxies. Its gravity is so strong that it bends the light from more distant galaxies, creating gravitational lenses. These lenses act like cosmic telescopes, allowing astronomers to see some of the most distant objects in the universe. By studying how light is bent, we can map the distribution of dark matter. The results reveal that the universe is a cosmic web of dark matter filaments, with galaxies strung along them like jewels on a necklace. The empty spaces between filaments are vast voids, nearly devoid of matter. This structure is a direct legacy of the quantum fluctuations from the Big Bang, amplified by inflation and gravity over billions of years. But the universe is not just a collection of galaxies and gas. It is also a stage for the most violent events known. Gamma-ray bursts, the most powerful explosions since the Big Bang, occur when massive stars collapse or when neutron stars merge. Within seconds, they release more energy than the Sun will produce in its entire lifetime. If one occurred within a few thousand light-years of Earth, it could strip our atmosphere and trigger a mass extinction. Fortunately, such events are rare. But they remind us that the universe is not a peaceful place. Supernovae, black hole mergers, and gamma-ray bursts are part of the cosmic cycle of destruction and creation. In the search for life, we look for planets that are not too hot, not too cold, and that have liquid water. The habitable zone around a star is the region where water can exist on a planet's surface. But as we've learned, even that is not enough. The planet must have a stable climate, a magnetic field to shield it from cosmic rays, and plate tectonics to recycle nutrients. Earth is so far the only example we have, but the discovery of water on Europa and Enceladus, of organic molecules on Titan, and of hundreds of exoplanets in their stars' habitable zones suggests that the conditions for life may be common. The question is whether life actually emerges wherever conditions are right. That is the question that drives astrobiology. One of the most promising places to search for life beyond Earth is Mars. The red planet once had a thick atmosphere and surface water. Rovers have found evidence of ancient riverbeds, lakebeds, and minerals that form only in water. But Mars lost its magnetic field billions of years ago, and the solar wind stripped away most of its atmosphere. The surface became a cold desert. Yet, beneath the surface, there may still be aquifers of liquid water, and life could survive in those deep, dark, warm pockets. NASA's Perseverance rover is currently collecting samples that could contain signs of ancient microbial life. A future mission will bring those samples back to Earth for analysis. The answer to whether life ever arose on Mars could come within a decade. Beyond Mars, the icy moons of Jupiter and Saturn are even more tantalizing. Europa has a global ocean beneath its ice crust, kept liquid by tidal heating. Jupiter's gravity stretches and squeezes the moon, generating heat that prevents the ocean from freezing. The ocean is in contact with the rocky seafloor, where hydrothermal vents may supply the chemical energy needed for life. NASA's Europa Clipper mission, launching in the 2020s, will fly by the moon dozens of times, mapping its ice shell and searching for plumes of water vapor. If it finds evidence of organic molecules in those plumes, a future lander could drill through the ice and sample the ocean directly. Enceladus, as we've seen, already provides direct evidence of a habitable ocean. The Cassini mission flew through its plumes and found hydrogen gas, a potential energy source for microbes. Enceladus has all the ingredients: liquid water, energy, and organic compounds. The next step is to send a dedicated mission to study the plumes more closely. A spacecraft could fly through them multiple times, collecting samples and analyzing them for signs of life. It would be like a cosmic fishing expedition. Titan is another prime candidate, but for a different kind of life. Its lakes and seas of liquid methane could host organisms that use hydrogen instead of oxygen, and that metabolize methane instead of water. The Dragonfly mission, set to launch in 2027, will send a drone to fly through Titan's thick atmosphere, landing at multiple sites to study the chemistry. It will look for both prebiotic molecules and potential biosignatures. If life exists there, it would be a second genesis, a completely independent origin of life. That would transform our understanding of biology and our place in the universe. Back at home, the moon is a natural stepping stone for exploration. Its south pole contains water ice in permanently shadowed craters. That water could be used for drinking, for growing food, and for splitting into hydrogen and oxygen for rocket fuel. NASA's Artemis program aims to establish a long-term presence on the moon by the end of the 2020s. From there, astronauts could travel to Mars. The moon also offers a unique platform for astronomy. Its far side is permanently shielded from Earth's radio noise, making it an ideal location for a radio telescope. Such a telescope could explore the cosmic dark ages, the period before the first stars formed, and possibly detect signals from beyond the visible universe. The universe is not silent. It is filled with electromagnetic radiation across the entire spectrum. From radio waves to gamma rays, each band tells a different story. Radio telescopes have mapped the hydrogen gas that fills the Milky Way. Infrared telescopes peer through dust clouds to see newborn stars. X-ray observatories spot the hottest gas, like the million-degree plasma in galaxy clusters. Gamma-ray detectors catch the most energetic explosions. But the newest window on the universe is gravitational waves. LIGO and Virgo have now detected dozens of black hole mergers and several neutron star collisions. These events produce unique signals that reveal the masses, spins, and distances of the merging objects. In 2023, a new array of pulsar timing arrays announced the detection of a gravitational wave background, a faint hum likely from the merging of supermassive black holes in the early universe. This is like hearing the background music of the cosmos, giving us a new way to study the evolution of structure. The study of the universe also forces us to confront the limits of our knowledge. The Big Bang Theory is extraordinarily successful, but it leaves the initial singularity unexplained. The laws of physics break down at that instant. Some theorists propose that the universe is eternal, cycling through big bangs and big crunches. Others suggest that our universe is just one of many in a multiverse, where different patches of space have different physical constants. We may never be able to test such ideas directly, but we can look for clues in the cosmic microwave background, the afterglow of the Big Bang. Tiny variations in its temperature encode information about the early universe. Future missions, like the Lightbird satellite, will measure the polarization of the CMB to search for evidence of inflation. If we detect the distinctive pattern of gravitational waves from inflation, it would be a smoking gun for a period of exponential expansion in the first fraction of a second. Another frontier is the nature of quantum gravity. General relativity describes gravity on large scales, while quantum mechanics rules the subatomic world. But at the center of a black hole, or at the beginning of the universe, these two theories collide. We need a theory of quantum gravity to understand what happens. String theory and loop quantum gravity are contenders, but neither has been confirmed. The most promising avenue may be through black holes themselves. Stephen Hawking showed that black holes are not entirely black. They emit a faint radiation due to quantum effects near the event horizon. This radiation causes black holes to slowly evaporate. But the information paradox, what happens to the information that falls into a black hole when it evaporates, remains unresolved. The answer may force us to rethink the nature of spacetime itself. Meanwhile, the search for extraterrestrial intelligence, SETI, continues. Radio telescopes listen for artificial signals from other civilizations. The breakthrough. Listen Project is scanning 1 million stars for signs of technology. So far, silence. But the lack of signals does not mean we are alone. It may be that intelligent life is rare, or that the timescale of civilizations is short, or that the universe is just too vast and the signals too weak. The Fermi paradox asks, if the universe is so big and old, why haven't we heard from anyone? Possible answers range from the Great Filter, something prevents the emergence of advanced civilizations, to the zoo hypothesis, they are deliberately hiding. We may not know, until we find a signal, or until we ourselves become an interstellar species. Beyond the search for life, there is the question of the ultimate future of intelligence. If civilizations survive long enough, they could spread across the galaxy, building Dyson spheres to capture the energy of stars, or engineering wormholes for rapid travel. Some physicists speculate that a sufficiently advanced civilization could even create a new universe in the lab, a baby universe that expands from a tiny singularity. That would be a form of cosmic reproduction. In that sense, the universe may be a multi-generational ecosystem of universes, each with its own laws. But let us return to the present. The James Webb Space Telescope, launched in 2021, is already revolutionizing our view of the early universe. It has detected galaxies that formed less than 400 million years after the Big Bang, when the universe was only 3% of its current age. Those galaxies are surprisingly mature, with structures that challenge our models. Webb is also studying exoplanet atmospheres, detecting water, carbon dioxide, and methane in the skies of worlds like TRAPPIST-1e. It may find biosignatures, gases like oxygen and methane in combination that could indicate life. The coming years are the golden age of astronomy, with more data and more answers than ever before. As we explore, we must remember that we are tiny specks on a small planet orbiting an unremarkable star in a typical galaxy. But that tiny speck has developed the ability to understand the cosmos. We can trace our origins back to the Big Bang, see the formation of atoms, stars, and planets, and look forward to the ultimate fate of everything. That is a profound achievement. The universe works through laws that we can discover, and each discovery reveals how we fit into the grand narrative. In the end, the story of how the universe works is also the story of our own existence. The carbon in our bones was forged in stars that died long before the Earth formed. The oxygen we breathe was created by the same stellar alchemy. The water in our oceans came from comets and asteroids. We are, quite literally, made of stardust. And our curiosity is the universe's way of looking at itself. Every time we ask a question, every time we build a telescope or send a probe, we are continuing a process that began with the first sparks of consciousness. The universe is not a machine to be merely described. It is a story to be told, and we are both the storyteller and a part of the story. So the next time you look up at the night sky, remember that the light from those distant stars has traveled for thousands or millions of years to reach your eyes. Each photon carries a message from the past. The Milky Way is a river of stars and gas and dark matter flowing through the cosmos. And somewhere out there, perhaps, another intelligence is looking at the same sky, asking the same questions. Whether we ever find them or not, the search itself is what makes us human, and that is how the universe works.
Amid the silent expanse of our solar system lurks Mars, a world of deep mystery and rugged beauty. With its purple dunes and ancient valleys, Mars tells of its tantalizing past. It's a planet where sunsets color the sky blue, where towering dust devils run across barren lands, and where the remnants of water streams silently tell the story of bygone days. Here, amid the red dust, lies the enigmatic brain terrain, a geologic marvel that defies explanation. Its intricate patterns, reminiscent of the complex folds of the human brain, remain one of Mars' most challenging mysteries. What forces created these enigmatic formations? Are they the key to unlocking the secrets of Mars' climatic past? As the sun dips below the horizon, the Martian sky transforms. casting blue light over the alien landscape. The scars of ancient rivers and cracks of dried mud tell a story of a time when water flowed freely on Mars, when the planet experienced the changing of seasons, and when this world may have been more Earth-like than we could have imagined. Yet for all its wonders, Mars is a stark reminder of its alien nature. Then we venture to the enigmatic Saturn, where atop its North Pole, a geometric marvel, the hexagonal storm, defies explanation. What forces of nature sculpt this bizarre phenomenon? Can we unlock the secrets of Saturn's hexagonal riddle? Our odyssey continues as we seek the latest real images of Uranus. This elusive ice giant, shrouded in mystery, reveals new truths through the eyes of modern exploration. What will we discover in the unseen details of its atmosphere and rings? Finally, we dive into the azure depths of Neptune, revealing its true colors, a world far beyond our own, where the winds howl with ferocity and the skies tell tales of ancient ice and gas. What mysteries does this distant giant hold in its cerulean hues? Join us as we traverse the cosmos, seeking answers and marveling at the beauty of the universe. This is not just a journey through space, it's an exploration of the unknown, a quest for knowledge, and a tribute to the human spirit's unending curiosity. Welcome to our documentary series, where the mysteries of the universe unfold before your eyes. Beneath the purple skies of Mars lies a canvas of geologic mysteries. Among them is the brain terrain. These complex patterns, reminiscent of the cerebral cortex, sprawl across the Martian mid-latitudes. Their origins are shrouded in mystery. What processes could have created such complex patterns? Scientists suggest that it's sublimation, the conversion of ice directly into vapor, that plays the key role here. Although the exact process remains cloaked in mystery, it's most likely the relentless interaction between the underground ice and the thin Martian atmosphere that forms the intricate patterns. But Mars is not a quiet world. It breathes and moves. Dust devils, those towering columns of cloying dust, rising kilometers into the rarefied atmosphere, are not just a spectacle of nature, but the architects of the Martian surface. They crisscross barren landscapes, leaving behind dark trails that testify to their passage. These ethereal giants, born from the interaction of heat and wind, reach more than 2 miles in height and are larger and more dramatic than their terrestrial counterparts. And then, as the Martian day fades, the sky transforms. A Martian sunset bathes the landscape in an ethereal blue light that contrasts sharply with the familiar red and orange hues of daytime. This phenomenon arises due to the unique interaction of sunlight with the atmosphere of the red planet, filled with dust of iron particles. As it passes through, the red part of the visible spectrum of sunlight is scattered by the dust particles, leaving only a mesmerizing blue glow. Although this scattered light colors the sky red, at sunset and night it transforms into shades of blue. But the mysteries of the Martian atmosphere don't end there. The interesting phenomenon of Mars' green glow, recently captured by NASA's Odyssey orbiter, provides a glimpse into the unique characteristics of the Martian atmosphere. This glow, observed from orbit, is the result of atmospheric processes that are common throughout the solar system, but manifest themselves differently on each planet due to variations in atmospheric composition and density. During the day, sunlight interacts with the Martian atmosphere, breaking down CO2 molecules through a process known as photodissociation. This releases individual atoms, which, when they hit the night side of the planet, recombine into different molecules while emitting light. On Earth, this phenomenon produces a whole spectrum of colors. But on Mars, the predominant color is green. This green glow is primarily due to the recombination of CO2 molecules in the upper atmosphere at an altitude of between 25 and 90 miles. Interesting studies have revealed an additional glow at lower altitudes, resulting from the recombination of oxygen atoms. This secondary glow, visible during the Martian summer, is concentrated in the polar regions, where atmospheric currents converge. The intensity of this glow varies with the time of year, alternating between the northern and southern hemispheres. The thinness of the Martian atmosphere compared to Earth's allows these luminous phenomena to be observed and studied more directly. It's also allowed the detection of other emissions, such as nitrogen oxide emissions in the ultraviolet spectrum, further enriching our understanding of the composition and behavior of the Martian atmosphere. Such atmospheric studies not only shed light on the processes that shape the Martian environment, but also provide valuable insights into the planet's past and present climatic conditions. Speaking of which, the Martian landscape, with its vast deserts and towering volcanoes, contains a wealth of clues about the planet's climatic past. Among them are signs of seasonal changes that have shaped the surface for millennia. The presence of features such as mud cracks, discovered by the Curiosity rover, which bear a striking resemblance to similar objects on Earth, suggests the presence of liquid water in the planet's past. In particular, the mud cracks are thought to have formed over many Martian seasons, indicating a cycle of wet and dry periods that Mars once experienced. Further evidence of Mars' dynamic climate can be found in the remains of ancient glaciers in the planet's mid-latitudes. These fossilized archives, imprinted into the Martian terrain, tell of a time when water ice slid across the planet's surface, carving furrows and transporting sedimentary rocks. These glaciers, like their terrestrial counterparts, shaped the terrain, leaving behind traces of their presence in the form of moraines and carved valleys. Such activity suggests that Mars has undergone significant climatic changes, perhaps similar to the glacial and interglacial periods seen on Earth. The presence of sulfate in the mud cracks adds another layer to our understanding of Mars' water history. Mud cracks, like those found on Earth, are formed by the drying of sedimentary rocks, indicating the presence of standing water that periodically evaporates, leaving behind these prominent patterns or subsiding beneath the surface. The detection of sulfates in these formations indicates that water interacted with the Martian soil, resulting in the deposition of minerals. The varying levels of these sulfates, combined with the pattern of mud cracks, paint a picture of a planet where water levels rose and fell, creating conditions conducive to chemical reactions that could even support the precursors of life. Clearly, it's the search for water on Mars that is a key aspect in understanding the planet's climate, geologic history, and potential for habitable life. Recent discoveries have shed light on the presence of water in various forms and locations on Mars, significantly changing our understanding of the red planet. On Mars, there are a great many geologic features that indicate the presence of water in the past. The discovery of ancient lake beds, river valleys, and outflow channels indicates that at one time, water flowed freely across the planet's surface. These features suggest that Mars once had a warmer and wetter climate, capable of supporting liquid water on its surface. The presence of sedimentary layers and mineral deposits in these ancient lakes and river valleys further supports the idea of prolonged water activity that may have lasted thousands or even millions of years. One of the most revolutionary discoveries is the discovery of water ice near the equator of Mars. Traditionally, ice was thought to be found only in the polar regions of Mars, where it's visible on the surface. However, radar surveys and analysis have revealed subsurface deposits of ice at lower latitudes, including near the equator. This refutes previous ideas about the climate of Mars and suggests that water ice is much more widespread across the planet than previously thought. The implications of equatorial ice extend to the climate history of Mars and its potential habitability. Equatorial ice deposits indicate a more complex hydrologic cycle on Mars than previously thought. This could mean that in the past, Mars had a climate more similar to Earth's, with water cycling between the atmosphere and the surface. However, such a presence does not at all raise the possibility that conditions suitable for life existed on Mars in the past, much less in the present. Water is a key component of life, but such a contrasting climate change cannot offer much chance for a long process of development of any life forms. The search for biosignatures such as special minerals, organic molecules, or erosion patterns that may indicate past biological activity continues. Although no conclusive evidence of life on Mars has yet been found, the presence of water in various forms still retains a minimal possibility. Still, these water ice deposits could serve as a valuable resource for future human exploration and colonization of the planet, providing water for drinking, agriculture, and fuel production. Taking a closer look at the mineralogical landscape of Mars, we see that it's a stark contrast to the rich diversity found on Earth. About 6,000 different minerals have been discovered on our home planet, testifying to the dynamic geologic processes on Earth and the complex interaction between the biosphere and geosphere. These minerals have not only been formed by abiotic processes, but have also been significantly influenced by the presence of life, which has contributed to the diversity of minerals through various biochemical interactions. By comparison, after 5 decades of research, only 161 minerals have been identified on the Martian surface. This divergence in mineral diversity is not just a numerical gap. It tells us a lot about the differences in the geological activity and history of the two planets. The scarcity of minerals on Mars has profound implications for our understanding and the planet's potential to support life. The diversity of minerals on a planetary body is often a reflection of its geologic and environmental dynamism. On Earth, plate tectonics, water availability, and atmospheric processes contribute to the wide range of physical and chemical conditions that are so essential for the origin and maintenance of life. Complex organic molecules, including the precursors to DNA, often require diverse chemical environments and catalysts. The limited mineral diversity on Mars, therefore, raises some questions about the habitability of the planet as a whole. The lack of diverse minerals on Mars also indicates the planet may have had a more monotonous geologic history compared to Earth. However, is it as quiet and peaceful as it appears? Recent studies of the internal structure of Mars have led to interesting discoveries, particularly through the analysis of seismic data. The InSight mission played a key role in this discovery before its completion, detecting what's believed to be the largest earthquake ever recorded on Mars. This earthquake, which lasted about 6 hours, did not fit the typical profile of a meteorite strike because no crater was left behind, suggesting it originated deep inside the planet. The magnitude of the quake, which was 4.7 on the Richter scale, hints at a significant geologic activity beneath the surface. Unlike Earth, Mars lacks plate tectonics, raising intriguing questions about the mechanisms causing these earthquakes. The lack of plate tectonics suggests that Martian earthquakes may be related to internal stresses or other geologic processes that we've not yet fully understood. Volcanic activity on Mars, both recent and ancient, has left indelible marks on its surface. Recent studies have found at least 40 different volcanic events, some of which occurred only a few million years ago. In addition, the discovery of unusual polygonal structures beneath the surface, found by ground-penetrating radar from China's Churong rover, indicates a history of thermal contraction and expansion and speaks to the planet's former volcanic activity. These structures, ranging in size from a few inches to a few feet, have been found at depths of about 100 feet. Obviously, a dramatic change in climate or some cataclysmic event has caused these deposits to be so deep beneath the planet's surface. The region known as Noctis Labyrinthus, with its vast network of valleys and canyons, is further evidence of Mars' volcanic past. Located near the volcanic Tharsis Plateau, home to the solar system's largest volcano, Olympus Mons. This region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by ESA shows how the stretching and bending of the Martian crust in this region, resulting in the formation of deep valleys and canyons, is evidence of the planet's active geologic past. The release of water during organic eruptions may explain the presence of ancient river valleys and lakes, providing a glimpse into times when Mars may have been more Earth-like, with a warmer and wetter climate. Understanding the planet's volcanic history not only sheds light on its past climate and potential for life, but also helps in future research, as regions with past volcanic activity may hold clues to the planet's habitability and the availability of vital resources. Speaking of livability, it's impossible not to mention the recent successes in the production of oxygen on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an achievement in space technology, successfully producing oxygen from Mars' carbon dioxide-laden atmosphere. Installed aboard NASA's Perseverance rover, MOXIE operates efficiently in a variety of Martian conditions, both day and night, and in different weather states of the planet's atmosphere. Its ability to convert CO2 into oxygen through the process of solid oxide electrolysis is a significant technological achievement. By heating the Martian atmosphere to 800 degrees Celsius, MOXIE decomposes CO2 into oxygen ions and carbon monoxide, and then recombines the oxygen ions into breathable O2. This process has been shown to achieve the required oxygen production and purity despite design trade-offs due to the mass, power, volume, and cost constraints associated with space missions. The success of MOXIE has profound implications for the future of human exploration and potential colonization of Mars. The ability to produce oxygen on Mars paves the way for a sustainable human presence, reducing dependence on Earth for critical life support resources. The study concludes that a large-scale version of MOXIE could generate tens of tons of oxygen, essential not only for astronauts' life support, but also as a critical component of rocket fuel. Such a capability would significantly reduce the logistical and financial burden of transporting oxygen from Earth to Mars, which would otherwise require launching hundreds of tons of the material into space at an exorbitant cost. By providing a reliable supply of oxygen, systems like MOXIE could support longer missions, larger crews, and even permanent settlements on Mars. In addition, the technology can be adapted to produce other necessary resources, such as water and fuel, taking a significant step toward realizing the dream of a self-sufficient human presence on the Red Planet. Speaking of the Perseverance rover, we should also mention its Ingenuity helicopter, which has far exceeded the original parameters of its mission on the Martian surface. Built just for a brief technology demonstration, Ingenuity was only supposed to make 3 flights within 30 days. However, it shattered those expectations by flying 72 missions over more than 1,000 Martian days, demonstrating its resilience and adaptability to the harsh Martian environment. This achievement was not only an important milestone in the aerial exploration of other planets, but also laid the groundwork for future missions. Ingenuity's journey was not without its challenges. It encountered and overcame numerous technical problems, including communication outages and unexpected landing scenarios. Despite these challenges, Ingenuity continued to push the limits of what was possible, and even set a new range record on one of its flights. The vehicle's ability to survive and operate through Martian dust storms, extreme temperatures, and even sensor failure speaks to the reliability of its design and the team's careful planning. However, the mission ended in an unforeseen way when a significant part of the blade of one of Ingenuity's rotors was damaged, making further flight impossible. This incident marked the official end of Ingenuity's Mars mission. The helicopter's final flight took place in January 2024. However, the termination of Ingenuity's missions does not take away from its outstanding achievements and the invaluable data it provided. NASA has already begun applying lessons learned from operating aircraft in extraterrestrial environments to upcoming missions, including the Dragonfly mission to Titan, Saturn's largest moon. The success of Ingenuity has opened the door to more ambitious use of aircraft for tasks such as sample retrieval, which could significantly increase the efficiency and scope of exploration of other planets. During its long stay on the Red Planet, the Perseverance rover has accumulated a considerable amount of samples of Martian rock materials. However, it's worth noting that the endeavor to return samples from Mars to Earth is both the pinnacle of scientific endeavor and the nadir of logistical challenges. The financial implications are staggering. According to recent estimates, the costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, totaling up to $11 billion. The complexity of safely extracting samples from the Martian surface and transporting them back to Earth involves multiple spacecraft and precise robotic operations. This task requires not only unprecedented precision engineering and navigation solutions, but also significant financial outlays, which raises questions about budget allocation and priorities in space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge. The ongoing debate over international cooperation in Mars exploration is multifaceted, involving political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific return on missions through diverse expertise. On the other hand, comparing the successes of collaborative efforts, such as the International Space Station, against the backdrop of some international constraints, highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another, but not the last, test in our path is that as Mars becomes a center of exploration and potential colonization, the problem of space debris is becoming increasingly important. Debris accumulation in Martian orbit can pose a hazard to spacecraft, impede navigation, and jeopardize missions. This problem is not just theoretical. The proliferation of debris around Earth has already created an urgent need for sophisticated tracking and avoidance maneuvers. In turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris, and possibly the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. Mars colonization, once the stuff of science fiction, is increasingly entering the realm of possibility, thanks to technological advances and scientific discoveries. The successful demonstration of in situ resource utilization through experiments such as MOXIE, the potential to use local materials for construction, and advances in life support systems are gradually laying the groundwork for sustainable human presence on Mars. However, the vision for colonization goes beyond technological challenges to include ethical, social, and environmental considerations. The responsibility of extending humanity's footprint to another planet raises questions about how we steward the Earth and the extent to which we will be able to apply these lessons to the New World. The future of Mars exploration is rich in promise and fraught with challenges. As we stand at the threshold of these endeavors, the collective wisdom, ingenuity, and cooperative spirit of the global community will play an important role in overcoming these challenges and realizing the dream of expanding humanity's presence beyond Earth. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a parero, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Triton and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Triton, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Triton's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Triton and Saturn. Could this drift affect Triton's internal dynamics? And perhaps even its potential for the existence of life. An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Triton a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Triton. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle. It's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age. expand their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1,000,000 miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogencation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus orbiter and probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with a Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which are affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climatic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of spacetime to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown, guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new, uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes. This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1. The infinite universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2. The post-inflationary multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life, of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, They share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3. The Many Worlds Interpretation of Quantum Mechanics. Perhaps the most disconcerting of Tegmart's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the Many Worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the Many Worlds interpretation, at the moment of the coin flip, the universe is split into two, one where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe, and the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4. Ultimate Ensemble. The fourth level of Max Tegmart's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible, but this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth